In this project, our driving question was, what can we learn about environmental gases and open source hardware from sending a helium balloon into the upper stratosphere? In the Pie in the Sky seminar, we worked on labs that would improve our understanding of the various gas laws that would interact with the balloon and the sensors. These included studying the ideal gas law in addition to learning about the layers of our atmosphere. Each group of students was assigned to master a certain part of the technology that would be in the payload box. The first item that we put in our payload box was a Vernier LabQuest 2. We also packed in a temperature probe, UVB light sensor, a barometer, an Arduino microcontroller with a Vernier probe shield. Using code by Vernier that we modified, we attached a magnetic field sensor to record data each minute during the flight to EEPROM memory on the Arduino. Next, we added a GoPro camera to record a video of space while the balloon was up in the atmosphere. A spot tracker GPS was involved to tell us where the balloon was when it landed. We put a marshmallow on a spike off the box that we watched with a camera hooked to a Raspberry Pi microcomputer. Raspberry Pi is an open source microcomputer that we programmed to take pictures every minute for 4 hours on device startup. We laser engraved our school's logo and tagline onto a piece of wood, and we extended it off the box so that it would be in the GoPro's video. The box was painted with a pig motif so that we could identify it upon landing. The parachute was attached so that when the balloon burst, the box would slowly descend down to Earth instead of a simple, speedy drop. We utilized a program from habhub.org that would take into account the jet stream, the ascent and descent rate, the time and day of launch, burst altitude, and location to get an estimate of where the balloon would fly, pop, and land. We tried our best to have it land in a field. We saw that if we drove out to North Branch, Minnesota, we could get it to land just southwest of Rice Lake.
I've always wanted to see pigs fly. Love it.
Alright. 10, 9, 8, help me guys. 7, 6, 5, 4, 3, 2, 1. Let her go. There he goes. Awesome.
We determined the max altitude for launch using initial GPS altitude. Our altitude measuring equipment only measured at 12,000 meters, so we had to drive an average ascent rate using our initial data. We graphed time in seconds versus altitude for the first 12,000 meters of our launch, finding this to be a linear relationship with a slope of 5.42 meters a second. With that information, we could calculate how high the balloon went, since the exact time the balloon popped was recorded by our onboard GoPro camera. We know that from the time the balloon was launched to the time it popped was 94 minutes, so we converted minutes to seconds and took 5.42 multiplied by the total time in seconds. We found the balloon went roughly as high as 31,000 meters.
The data that we analyzed was the relationship between altitude and temperature. Our graph shows that as the balloon rises, the temperature gets colder until around 20,000 meters. This, we learned, is the same area where the troposphere ends and the stratosphere begins. As the balloon reached the stratosphere, the temperature began to rise. Most sites say that in space the temperature will be cold, then will get warmer in the stratosphere because of the ozone layer. In the ozone, it takes air molecules and turns them into heat, which makes it hotter. Our data proves that to be true. If we could remedy our data in any way for our next launch, I would say we could send up a bigger balloon to make it go higher, and we could see how warm or cold it really gets.
Altitude versus air pressure. Initially, the plan was to use the equations on the screen to derive altitude using the air pressure, since our launch included no way to find altitude using a GPS. However, due to the equipment issues with our barometer, We had to use the equation to instead derive the pressure with varying altitudes. We used the two equations on the screen to solve for pressure, and then plotted the points for pressure versus altitude. As you can see on our graph, there are three distinct regions. Those regions represent the different equations we had to use due to a changing standard temperature lapse rate. For the first 11,000 meters, the lapse rate was constantly changing. We had to use the first equation for this set of data.
For our section of the project, we compared the altitude of the balloon versus the amount of UV radiation that was present in the atmosphere. To collect the data for this experiment, we used a Vernier UVB sensor attached to a Vernier LabQuest device. Every minute, the sensor would take a reading of the UV radiation levels and save them. Our initial hypothesis was that the UV levels will slightly increase as the balloon ascends, and significantly increase when the balloon passes above the ozone layer. There was no visible relationship between the two variables that we tested for. We noticed that our data was inconsistent and did not agree with our hypothesis. We think this is because of the balloon spinning while it was floating around in the atmosphere. Sometimes the sensor would be blocked from the sun by the boxer balloon, resulting in lower UV readings, but when it was exposed to the sun, it would be much higher. One way we could fix this is to dangle the UV sensor from the bottom of the box so it won't be blocked from the light.